In this video, let's talk about partial fraction expansion, and specific how to solve for the coefficients. So this one is going to be equal to a over s plus 3 plus b over s plus 2 plus c over s plus 1, right? Now what our task now is to solve for a, b, and c. And the reason we do this is oftentimes for either integration, if we wanted to integrate this with respect to ds, or if we wanted to transform into the Laplace domain. So like a Laplace inverse of this may give us the time solution. So say this was like f of s is equal to this thing. Then if we did Laplace inverse of this thing, then we get time domain so that we're in f of t. So that could oftentimes be like a solution to a differential equation or something of that nature. Cool. Let's get cracking. So what we're going to do is have this set equal to the whole thing, s plus 4 over s plus 3 multiplied by s plus 2 multiplied by s plus 1. Now, if we want to solve for a, what we're going to do is multiply both sides by s plus 3. So what's going to happen is this s plus 3 and this s plus 3 are going to go away. This s plus 3 is going to go away. And we're going to have a plus b times s plus 3 over s plus 2 plus c times s plus 3 over s plus 1. And this is all going to be equal to s plus 4 over s plus 2 times s plus 1. So now, what if we just evaluate both sides at s equals, let's say -3. So evaluating at -3 is the root here. So this term's going to go to 0. So the whole term goes to 0. This term goes to 0. So the whole term goes to 0. And we're just left with a is equal to s plus 4 over s plus 2 multiplied by s plus 1, all evaluated at s equals -3. So we get, if we plug in s here at -3, we get 1 over s, -3 plus 2 is -1. -3 plus 1 is -2. And we get a is equal to 1/2. And following a similar methodology, we can solve for b and c. So let me go ahead and copy this. Paste it here. But now, instead of multiplying by s plus 3 on both sides, we're multiplying by s plus 2, and we're going to evaluate at s is equal to -2, right? So the shorthand way of doing this is doing s plus 4 times whatever's under the coefficient that you're trying to find, so s plus 2, over the whole denominator, s plus 3, multiplied by s plus 2, multiplied by s plus 1. We know a and c are going to go to 0, so we get this is just equal to b. We're multiplying both sides by this, so those cancel, and that's equal to b. And so we get these two to cross out, and we have s plus 4 over s plus 3 and s plus 1. And again, we have to evaluate at the root. So when is this equal to 0? That's s equals -2. So those things equal to b. What about c? C is equal to s plus 4 over s plus 3 times s plus 2. So you can think about just removing the denominator that's the coefficient that you want from this side, and then evaluating at what makes this equal to 0. So we're going to evaluate here at s equals -1, and that's equal to b. Or sorry, that's equal to c. So b is going to be equal to -2 plus 4 is 2. -2 plus 3 is 1. -2 plus 1 is -1. So we get b equals -2. And then plugging in -1 here, we get 3 over -1 plus 3 is 2. -1 plus 2 is 1. We get 3/2 for C. So in total, we can write our partial fraction expansion as A, which was 1/2. So 1/2 over, and we had that originally over s plus 3, plus, and then we need b, so it's -2. So let's say -2 over s plus 2, and then plus 3/2 over s plus 1. And this whole thing is equivalent to the original one that we had, which was s plus 4 over s plus 3 multiplied by s plus 2 multiplied by s plus 1. So now that we're in this form, we can easily find the integral. Doing that would just be 1/2 ln of s plus 3, right? And then this one is minus 2 ln of s plus 2, and this plus 3/2 ln of s plus 1. And then we add a plus c if we're trying to find the integral. Now what if we're doing the Laplace inverse? This is equal to 1/2 e to the negative 3t minus 2e to the negative 2t, and then plus 3/2 e to the negative t. And all this is multiplied by the unit step function because the Laplace transform is one-sided. And so yeah, this is why we use partial fraction expansion. And if you get really quick at this, you can turn any sort of partial fractions into the coefficients and expand the form and do these steps really quickly. So say we had like s plus 3 over s plus 8 and s minus 4. So this would be equal to a over, let's see, s plus 8 plus b over s minus 4. So solving for a is equal to, we take out the denominator that is under here in this one. So we have s plus 3 over s minus 4. And then we evaluate at what makes this equal to 0. So s equals -8. And now b is equal to s plus 3. Take out the denominator you don't want. So over s plus 8. So you take out the denominator that's the one that's under the coefficient that you want, and you leave the other one, and then you evaluate at what makes this denominator equal to 0. So s equals 4. We solve those out super quickly. And yeah. Now, what about the case when we have like a repeated root? We can use this methodology and then kind of backtrace. So if we had s plus 4 over s plus 1 quantity squared, this is equal to the expansion form a over s plus 1 plus b over s plus 1 quantity squared. So we can only use this residue formula for the highest power denominator. Here we have a highest power denominator of 2, right? So if we found b equals s plus 4 over s plus 1 quantity squared multiplied by this denominator, multiplied by s plus 1 squared, and we evaluate at when this is equal to 0, so s equals -1. And the reason this works is because if we multiply both sides by s plus 1 quantity squared, then one of the s1s in the denominator goes away, but you're left with 1 in the numerator still for this, and you have s plus 1 times a, and then we evaluate s equals -1, that goes away, so this whole term goes away. And so we solve for b, and we get this goes away, and b equals -1 plus 4, so b equals 3. So now we have s plus 4 over s plus 1 quantity squared is equal to a over s plus 1 plus 3 over s plus 1 squared. And what we can do is evaluate at an easy s number and just solve for a. So let's choose s equals 1, and we get, so from here we solve where s is equal to 1 and we solve for a. So we get 5 over 4 equals a over 2 plus 3 over 4. Subtract 3 over 4 on both sides. We get a over 2 is equal to 2 over 4 is equal to 1/2. So a over 2 equals 1/2, a equals 1. So now we have a equals 1, b equals 3, and the expansion is 1 over s plus 1 plus 3 over s plus 1 quantity squared. And this is much easier to take a Laplace inverse on. We get the quantity e to the negative t plus 3t e to the negative t. And this is multiplied by the unit step function since the Laplace transform is one-sided. And that's our time domain answer. Say if our whole thing f of s was equal to this, then f of t would be equal to this. Cool. So in this video, I talked a little bit about the residue formula and how to solve for the coefficients in partial fraction expansion, and I hope you enjoyed. Thank you so much for watching.